And then we're going to start into solubility. Solubility is yet another kind of application of equilibria. It's a little bit more straightforward than the acid-base stuff. We don't have to worry about buffers. We don't have to worry about titrations. The one issue that does pop back up is coefficients, though. So when we're looking at solubility, you must make sure that you include those coefficients in your change for your ice charts, as well as in the equilibrium expression. All right? The rest of it is pretty much just kind of language, getting through the English of what you're solving for. Okay? So where we ended yesterday was looking at the bulk of this slide. We went through and determined the pH of that 1 liter solution. Thankfully, that was just a straight ice chart. We didn't have to do anything fancy with that. We just said, oh, it's an ice chart. We went through and plugged through it just like we would normally. Okay? However, when we shifted to A, we entered into a different realm because we're now adding a strong acid to that solution. The acid completely ionizes and is going to react with individual species that are present in the solution. Okay? What do acids tend to react with? It's not even tend. What do they only react with? Bases. So what we had to do in that case was go through and have that strong acid react with the weak base, okay, in a non-equilibrium reaction to generate or determine what our initial concentrations were so that we could then go through and solve an ice chart. Okay? So that was a pretty lengthy process. We introduced the concept of this new table, calling it the barn M chart, so we could do a barn mice chart if you wanted for your buffer solutions. All that is a way to format and organize your calculations. The calculations that you're doing in that chart are no more difficult than the limiting reagent calculations you've now had to do in lab, at least for one experiment, and you've done in 151, presumably multiple times. That's something rattling over here. Hi. So it's up to you if you want to use that or not. Yeah, it was. Oh well. After that, we could then go through a couple of these other examples. So when we look at part B, right, it says determine the pH. So now again, if we want the pH, what do we need to solve for? Concentration of H+. Once we know the concentration of H+, we can then say that the pH will equal the negative log of our concentration of H+. Okay? So we can go through the rest of that question. It says if 0.01 moles of HCl are added to 1 liter. What is HCl? It's a strong acid, which means it completely dissociates into the ions, which means we don't have to worry about any equilibria. And what ends up happening, the concentration of H+ ends up equaling the concentration of HCl to start with. Okay, so if we take a look at B, I know I've got them kind of organized weird up on the board here. Take a look at B. How did I set it up? The very first thing I did was convert the information out of the question. Okay? Get it into a format that now I can easily reference, assuming that I actually translated it properly. The next part is then coming up with an equation. You'll notice I asked up here, what arrow? Okay, we just answered that question. What arrow should we use there? Is this an equilibrium reaction? No, it's a strong acid, which means it completely dissociates. It's a unidirectional arrow. It only goes forward in this case. Okay? At that point, since we know that, we don't have to do any kind of barn charts or ice charts. We know the H+ completely converts over to, our hydrogen chloride completely converts over to H3O+ or H+, depending on your perspective. So we can then determine the concentration of H+, take the negative log of that, and what do we get for an answer? Oh, I know that one. That one's 2. Okay? So no ice charts, nothing fancy like that. That is something that we've seen in chapter, if I get the numbers backwards, 15. Okay, that's ultimately a chapter 15 solve. We don't have to worry about equilibria, just the strong acid. Okay? So if we look through what I ended up saying there, we don't have to worry about equilibrium. We just go through and solve for a concentration of H+, convert that into a pH. Fairly straightforward. Okay? The next part, question C. Determine the pH if we add 100 milliliters of a 1 molar strong acid to our initial solution of sodium fluoride. Okay. So again, what I went through and did in the case of C, sorry, I'm going to pull this down, is converted all of that initial information into a format that I could easily find and read. You'll notice at the very top, I put pH question mark. So now that when I go through and get an answer at the end, I can then go back and say, what did I want to solve for? There's no skipping to the answers. It's immediately going back and saying, what did I want? Am I there yet? No. Okay, now I can continue with my calculations. Okay. In this case, we're adding a strong acid to a weak base, which means that strong acid is going to completely ionize and react with whatever's present. Do we have a base present? Yes. So what happens? The strong acid reacts with that base. That's where we get the beginnings of our barn chart. Okay? So we have to go through and deal with that barn chart situation, or our limiting reagent calculation. Okay? Before we can do that, or before we just, how do you spell reagent? It's an R, you can figure out the rest. Okay? We need to use moles. When we do a limiting reagent calculation, all of our calculations based in 151 were based on moles. Okay? Not a concentration. We need to see how one molecule interacts with another molecule. Okay? So we have to convert all of our starting information into mole units. So we'll convert our HCl into moles. We'll convert our sodium fluoride into moles. And that's what these two calculations show. Okay? Questions about that first step? Okay. One of the things that might be kind of daunting, how long does this problem look to solve? Really, really long. It filled the whole board, right? Okay. You won't see a lot of these, but you are responsible for them. Okay. We can then go through and look to our reaction. What happens? HCl, being our strong acid, reacts with our sodium fluoride in a unidirectional reaction, not equilibrium. We generate HF. Why HF? HCl is an acid or strong acid, which means it donates hydrogen ions. Sodium fluoride, what does the sodium do? Completely dissolves off, so we don't have to worry about that. We're left with F minus. What does F minus need? Something positive to stabilize it. It's going to act as a base. What do bases do? Accept hydrogen. We do our transfer. We get HF, and if we wanted to balance it out as sodium chloride, we could. Okay, but again, both those ions are going to disappear from our equation. As far as the organization of the barn chart goes, we take a look at before we add the strong acid. Okay, so our strong acid in our B of our barn is going to be 0. After that, we'd fill in the rest of the information. There's only 2 other spots we have to worry about. Why do we not worry about the sodium chloride at all through this whole process? Doesn't affect the pH. Okay, sodium ion is the conjugate acid of a strong base. Doesn't affect the pH. Chloride ion is the conjugate base of a strong acid. Also doesn't affect the pH. So we don't have to worry about that ion. If we go back to what our calculation said for moles, did we have any HF to start? No. So we won't worry about the moles of our HF. Okay? Then we add the strong acid. So at this point, all we're doing is adding the strong acid. Everything else is going to be 0 because they aren't strong acids. Okay? So we'll put in our 0.1 moles of our acid, assuming I did all the calculations right. Looks right. We'll then go through and do the reaction. Okay? What we're going to do is compare the numbers that we've got across our table. In theory, it'll only be in our reactant columns that we'll be looking at. And we're going to subtract by the smallest number. Why the smallest number? That's the limiting reagent. Right? So we go through 0.1 versus 0.1, which is smaller. 0.1, so we will subtract 0.1 from both our reactants. Why do we add to our products? We can't create or destroy matter. So if we're going to remove matter from our reactant side, that means we must convert it into our products. Our product concentration is going to have to go up by that number. Yes? Okay. We can then look at the math behind that, add all the columns above it, and we take a look at our neutralization, so the N of our barn. What happens to the concentration of HCl? 0.1 minus 0.1 is 0. Concentration of fluoride. Also 0. Concentration of HF. 0.1 molar, or sorry, moles. Okay. We now have initial concentrations, which means now we can go into an equilibrium reaction, okay, if it's deemed necessary. So what we go through and do is convert all of our mole values into molarity. To do that, we have to divide by the total volume. You notice it's not 1 liter. Why is it not 1 liter in this case? We added 100 milliliters of our acid. Okay? It's an easy calculation to miss. Probably the most important part of your barn chart is dealing with that M portion. We have to make sure that you're using the total volume of the entire solution. Some cases the volume doesn't change, some cases it does. Watch out for that. At that point, we now have some concentrations that we could evaluate. What was our concentration of strong acid? 0 divided by 0.1, or 1.1? 0. 0 divided by 1.1? 0. What do we end with? We've got now some solution with just HF in it. What does HF do when it gets into water? Dissociates into its ions. So now what we have to do is move into an ice chart, starting with HF. We can add it to water. I left the water off this ice chart. Dissociates into our ions, and we get H plus and F minus. Yes, no, are you okay with that transition? Got at least one yes. Our initial concentrations, because I was not having a calculator, I just plugged in the value. Okay? Whatever my formula was over here. What's the initial concentration of H plus? Why is it 0? What happened to our strong acid? Completely removed. So our initial concentration of H plus is 0. Our initial concentration of fluoride ion. It says over here our initial concentration was 0.1. Should I plug that value in? Did I plug that value in? Let's try that answer first. No. Why not? What happened to my fluoride ion? Yeah, I saw you pointing. The fluoride ion reacted with the strong acid. The result of that is that there was none of that ion left, which means what's the initial concentration of the fluoride? 0. We completely neutralized it. Now we can go through the rest of the ice chart. We can look at our change. If we look at Q, Q would be equal to what? Our product over our reactants, which happens to be 0. What's the relationship between Q and K? Do we know what our K is? Assuming it's a reaction that actually functions, which everything you've got does, K has to be greater than 0, which means Q is by definition less than K, which means our product concentration goes up. We're going to come back to this box in a second. I'll also write it on the slides for those people at home. All right? To get our equilibrium concentrations, add our initial and our change. We end up with this expression. I know, this one looks a bit meaty. Okay? We can then write out our equilibrium expression for this reaction. Okay? When we go through and do this, it's our products over our reactants. What type of equilibrium did I look at? Or are we looking at here? The acidic one, which means this K needs to be AKA. So now we could go back and say, okay, what equilibrium constant am I given? We go all the way back to the very beginning. What type of equilibrium constant was I given? The Ka, which means I can directly substitute in. I don't have to do any weird conversions. Okay. So it's an interesting problem, because if we started this off and we looked at sodium fluoride and then this Ka, what would you immediately start to think? Probably would have to do a conversion, because sodium fluoride is a base. Turns out we added enough acid to overcome the effects of that base, and we don't have to worry about it. Okay? Go through, the very first thing we'll do is assume. Why assume? Makes all of our calculations easier. Okay? So if we assume x is much smaller than that value, we can then say that our denominator simplifies, and we can do our multiplication across, take the square root, and we get x equals... Anybody? Remember the whole part about me not calculating it? What was the number? Someone started shouting out.
0.76 or 77.
Anybody agree? After taking the square root. Did you square root it, Chase? Uh-oh. You're closer. Can I see your work? Chase, do you have yours in the car? Oh, you've got that smaller copy there. You got 0.007. Divided by 1.019.
I just started.
I got 11.
You didn't put one over 1.1? No,
1.1 over 0.1. And you multiply across that reaction. It flips and then forces that reaction. I simplified it out there. It's up to you how you want to do that. Okay, so what you guys should have gotten, now that I'm stealing the calculator, I get 0.027. Yeah. Oh no. 1.1 divided by 0.1 is 11. Times 6.8 times second, 10 to the negative 4. Did I do a mathematical mistake? Why don't from the beginning you just do 1 divided by 1.1 and get a number right? Oh, that's more. What number do you guys get? 0.086. I get 0.086 too. I did a typo in the calculator. I got 10 to the minus 5. So mathematically, I want to show you what I did here. We're a bit crowded on this. 6.8 times 10 to the minus 4 equals x squared over 0.1 divided by 1.1. To get this denominator to the other side, it's the same as multiplying by 1.1 over 0.1 on both sides. 1.1 times 0.1. Mathematically, it works out. If you don't like that, then do that division first, then multiply that by both sides. you'll end up doing the same thing as I've got here. I'll talk to you later about it, Chase. Okay, so the number we got was what? Okay. 0.1 divided by 1.1 is what? What? 0.090. Oh man, does the assumption not work? 0.086 divided by point. Oh man. Yeah. That's more than 5%. The assumption doesn't work. Son of a. So our assumption fails, which means none of that works, and we have to multiply this out the long way, which I'm definitely not going to be able to solve quick enough on this. We would get I'm trying to do way too many steps in my head. 10 to the minus 4, 1 over 1.1. Did I do that translation right? Yeah, I think I did. You'd then have to go through and solve for x. I'm not going to push that. Yes?
I think when you assume x is 0, because you're dividing by a fraction, I think you're going to flip it wrong from prior.
Let's just say a equals x squared over 0.1 times 1.1.
Yeah, so you would flip that.
Oh, you know?
And then bring it over.
You're right, I did do that mathematic flip incorrectly. So this is why you plug it into your calculator instead of trying to do it out cheating-wise. Does the assumption end up working then?
I think so.
It does end up working? Okay. Oh, well that's nice. So what do you end up getting for x then, if you do the assumption correctly? Now you get the 0.00. Okay. So that was x. What was x? What did we say x was? X is our concentration of H+. What did we want to solve for? pH. How do we get the pH? Negative log of that, which is 2.11. What was our initial pH? Does anybody have the notes from what we solved yesterday? We did go through and do that, right? Sodium chloride. That's something like 8, right?
0.08.
Okay, so what would we expect to happen if we start with an 8.08 pH solution and we add acid to it? What should happen to the pH? It should go down. What happened to our pH? It went down. Doesn't make sense. Yes. Okay? So be careful with your mathematic manipulations. Don't get too smart alecky with it like I tried to do. Okay? Questions on that? Yes? Do we always assume it goes to equilibrium? That's a harder question than you may ask. For this section of the problem, do we assume it goes to equilibrium? Where I'm pointing here, to solve for x. Absolutely. Why? How did we solve for x? We use the equilibrium constant. If you don't assume it goes to equilibrium, you cannot solve for x. You must assume. When we go through and look at the initial barn situation, do we assume it goes to equilibrium there? No. Why? Because it's not an equilibrium reaction. It's a strong acid reacting with a weak base. So we push that completely across, assume it goes completely through, look at our concentrations, then evaluate what happens at equilibrium. Okay? So sorry about the mathematical masturbation fail. Okay? But everything else worked, except for where I tried to shortcut math. Okay? Questions about that solve? How many of these would you expect on the exam? 1. Why only 1? Because it takes forever to go through and solve. Okay, you've got a lot of individual pieces. You have to do both the limiting reagent and the ice chart. Lots of places to make mistakes. I wouldn't expect you to go through and do it multiple times. You already saw that I made a math error. So when I go through and do this, where do you expect this problem to show up? Work or multiple choice? Work. Which means I would look at all your work and say, yep, all that work looked good, even though the answer I personally got was wrong. Okay? I'm grading you largely when it comes to this kind of stuff based on how do you set it up, are you setting it up, and thinking about it right. The rest of that math stuff does account for some portion of your grade, but it's not the entire portion. Okay? Does that make sense? Questions about that? I know, we got a little confused in that math area.
Would one like this still be worth it?
Yep. If it was a take-home part, you'd get like 4 or 5 of these problems, which I'm pretty sure you don't want. Trust me. I can make a take-home exam very hard. Okay? So what happens if we go through and did this and the acid didn't completely react with all of the fluoride? So let's say instead of it being 0.1 moles of acid that we added, it was 0.05 moles. How does that change anything? We wouldn't expect the pH to drop as much, and we would see that because our fluoride concentration, we'd still have some, and we'd have some of the HF, which means when we go into substitute, our initial concentrations, we'd have values in both those columns. Okay? We're still going to favor our Q being less than 0 or being equal to 0 because our H plus concentration would be 0. Should I change the numbers around so you get an idea of what's happening with that? Maybe get a second chance to solve that problem right mathematically? Yes, no? Yes. Okay, so quick change on numbers. We are going to do, how can I do this as minimally as possible? 0.5 molar HCl. What did I do? All I did was cut the molarity of the HCl in half. So when I go through to over here, change this number to 0.5 molar, which means this number becomes, oh, it's going to be a lot less. That didn't do as well as I wanted. 0.05. We've already seen I screwed up without the calculator. Somebody confirm, please. Confirm. Okay. Which means we go back up to our ice chart. We didn't touch the fluoride. All we've changed, let's go through and highlight it in black so we know what we're changing. Change the molarity of our HCl solution, which means this value changed. Does this number change? Our before for our sodium fluoride? No, we didn't touch it. How about the addition of our strong? Yes. That becomes, what happens in our reaction? In the reaction, what do? Divide by what? Or sorry, reaction is not a divide. It's a subtract. What do we subtract by? Why the HCl? smallest number is what I want to do here there. So minus 0.05, minus 0.05. What do we do to our product? Plus 0.05 because our concentration of our products has to go up if we lose our reactants. Add it up. What's our neutralization or moles for HCl? More math. What's the number here? What? No, really? Did I do it right? Maybe I did it right. What's this number? Convert to molarity. What's our molarity of our HCl? 0. What's our molarity for our sodium fluoride? This is where I screwed everything up before. Our total volume, did our total volume change?
Yes.
Did I touch the volume? No. We left the volume the same intentionally. I didn't want to have to do more calculations. What's that number? Because that's where I screwed up before. 0.05 divided by 1.1.
0.045.
Here, what do we get? 0.05. So we get 0.045 molar for that. Now when we go to our ice chart, we've got a couple ways that we could actually put this together. We have both sodium fluoride and hydrofluoric acid. Okay? So we could look at the equilibrium of sodium fluoride going to HF, or we could look at the equilibrium of HF going to sodium fluoride. Okay? Both options are valid because both concentrations are present. It's up to us to decide which one we want to work with. Yes?
Would it still be valid if both concentrations were different?
Yes.
Just choose one?
Yep.
Because they're both there?
Yep, as long as they're both there, we can pick whichever one we want. Okay? It's really going to come down to what we're solving for at the end. What are we solving for? pH, which is concentration of H. Which equilibrium do I want to look at? Fluoride going to HF and OH, or do I want to look at HF going to fluoride and H+? My goal is to figure out the concentration of H+ so I can get a pH. Which equilibrium do I want to look at? HF. So we'll take HF going to H+ plus F minus. What's the initial concentration of HF? Go back to our barn chart, 0.045. Initial concentration of hydrogen ion. Initial concentration of fluoride. Our Q is still less or still equal to 1, which is still less than K. Products still go up. Okay? Go through and substitute. H plus times 0.045. This worked out even better than I could have imagined. We'll talk about in just a second here. What do? Assume X is much less than 0.045. If we go through and do that, what do we solve for X? X equals, saw someone mouthing it there, 6.8 times 10 to the minus 4. How do we know that? If X is much smaller than 0.045, 0.045 minus a small number is same thing. 0.045 plus a small number, same thing. Those terms cancel. We get X equal to 6.8 times 10 to the minus 4. Is that substantially smaller than 0.045? Yes. What does that mean? We now know what X is. What did we say X was? Careful. X was our concentration of H+. to get the pH, negative log of our 6.8 times 10 to the minus 4. What do we get?
3.7.
We added less acid in this case. What would we expect to happen to our pH? Well, first off, we added acid to a base solution. What should happen? pH should go down. If we compare it to our last situation, we added less acid than we did before. Should the pH go down as much or more than? Less than. Did it go down less than? Yes. Okay? Yeah.
Up there you have chlorine.
Yes.
0.5.
That comes from our barn chart.
That's concentration of HF.
That's the concentration for HF. Shift to our next column over. Concentration of sodium fluoride is, okay, and that's because it didn't all react. We looked at a case where we really did have a limiting reactant. Okay? Questions on that? Okay, we are going to come back to that exact solve, so good call on having me redo another one there. Okay? When we get to C, that was C. C plus a new one. Okay, we have to go through and do the barn chart and the ice chart. Must do the limiting reactant, then push through and see what happens once we've finished all of our chemistry. We can then go through and look at the equilibrium. Okay, when we get to D, it's still a strong acid and a weak base, which means we still must go through that pre-equilibrium barn chart. Okay, we have to see what happens. In this case, I say no equilibrium when we go through and solve. Why would there be no equilibrium? Well, let's take a look at the solve. Take a look at part D, just set up here. We want to solve for our pH. Converted everything into the text. That was in the text into a problem. We start off, because we're at that strong acid, weak base, or strong base, weak acid. Both do the same thing. Go through the barn chart. We need to convert to moles. So we convert everything over into moles. Okay? Again, I didn't solve for numbers, but this time, hopefully it won't bite me. I don't know. We'll see what happens. Okay? Once we've got our moles, we can start our barn chart. We're adding a strong acid to a weak base. What happens? The weak base does what? Accept a hydrogen. From our strong acid, we generate HF. Left over, we get the sodium chloride, spectator ion, we don't have to worry about it. Before we started the reaction, sodium fluoride was 0.1 moles, as we saw from our calculations. In the addition, we ended up adding 0.2 moles of acid. Okay, why 0.2? Well, we added twice the amount. We go through, do our conversions, okay, or do our reaction, do the subtraction. What do we get? Leftover HCl is 0.1. Sodium fluoride is 0. Sodium fluoride in this case, in question D, is the limiting reactant. We will generate HF in that process. We get 0.1 moles of that. We can then go through and convert to molarity, and we've got the molarity for all of these things. So now what do we evaluate? Do we look at HCl, or technically our hydrogen ion concentration, or do we look at HF? We look at just the HCl. Why? Because it completely ionizes into the acid concentration, whereas the HF only partially ionizes. Which one's going to generate the larger concentration of H+? The HCl. So we will evaluate the HCl only. Okay? We don't have to worry about the acid contribution from our HF. So that means we would then go through, solve for the molarity of H+, which in this case is the concentration of HCl left over. We can then go through and do the pH, negative log of our concentration. One thing to watch out for. This is not the initial concentration of H+, correct? Why is it not the initial concentration? Nope, at this point, when we're solving for H plus concentration, it is not the same as 1 molar. 0.1 divided by 1.2 is not 1 molar. Why not? It reacted in the process of this reaction. That was redundant. Okay? It went through a reaction with our weak base. So some of it was pushed into HF. So we lost some of that, which means when we look at our H plus concentration, we must be evaluating after the barn chart. Okay? Notice our volume is also different. We must account for that volume change. It's now 0.2 liters, not the 1.1 that we had up in D. Why? We added more acid. Okay? All sorts of tiny little steps that you have to watch out for and that you're careful putting through into it. Okay? Then if you assume everything else you did perfectly, you still have to enter it into the calculator correctly or you screw it up. Okay? And you technically lose all points or all the respect your students ever had for you. That was kind of funny.
I was scribbling too much.
That's
How
fine.
do you know that that one didn't go to equilibrium?
We take a look at the concentration of what's left over. At the end of that reaction, we can come down here. What do we have? This number represents the strong acid. What does this number represent? The weak acid. Which one is going to dominate? The strong acid. Why? Because it's a strong acid. Okay? So when we go through our reactions, we have to decide which one of these is going to become more important. We can go through it right around the equilibrium where it's very, very, very close, or sorry, the end point, where it's very close. Then we do have to take that into consideration. That's very, very rare. I won't ever test on that. Okay? In every other situation, we've so overwhelmed the concentration that could come from our weak acid that we don't have to worry about it when calculating our pH. Yes?
So because the strong acid is going to go to the left, right? That's why we get.
There's no point that you're going at the left. I don't know where you're getting left from.
Well, did you say that the HCl is going to dominate? So it's going to go to the left whenever it's a strong acid.
There's no left here. I don't know where you're getting left from.
To write the equation out.
What equation do you have to write out, though? It's HCl plus water goes to what? H plus, which is only towards the right. That is right, and that's your product side. There's no left in this at all. As soon as you've got a strong acid, you go directly to the H plus concentration, and you're done. There's no left at all in that. The only way you'd get left is by looking at an equilibrium. When you have a strong acid, and that's it that's left over, there's no left. Other questions? See the face, go for it.
Maybe you just already answered it and we'll just get.
There's a lot going through here, so that's fine.
C and D is basically asking the same thing if you look at the question. All
Yes.
the words are the same except for 100 milliliters into 200 milliliters.
Yes.
So how do you determine that, hey, I don't need to go through the other ice chart?
You go through the barn chart and look at it. Yeah. That's the only way you determine it, which is why in both cases, both C and D, both of them involve the barn chart. We know we don't have to do the equilibrium in the case of D because what's left over? Strong acid. If it's not left over, as the cases we had up here, we'd then have to go into an ice chart because there's no strong acid. If we go back to D, what was our concentration of our strong acid at the end of our reactions? 0. There's no equilibrium. Or, sorry, there's no non-equilibrium. That was bad. Double negative. Okay? We end up having to do an equilibrium because we don't have a strong acid. When we go through and take a look at D, what do we end with? Strong acid. Yes, we have the weak acid, but this is where we get to decide which one is going to contribute most to the H plus concentration. The strong acid, because its equilibrium constant is massive. Really, really, really big. Where's the equilibrium constant for for our weak acid is so small, it doesn't generate as much of the acid ion. Okay? Yes?
I think what she was trying to say with the left reaction is you put like chloride plus the water, and you made the arrow go to the left when you use HCl plus OH. Like that's what's in minus. That's what I'm confused.
Okay, so I think you might be referring to, I'll bring that back down. Actually, I think I can do this on this. So if we take HCl, so let's draw that out. What happens when HCl hits water? Dissociates into H plus and Cl minus. Okay? We could then go through and look at the equilibrium. What effect does that have? I don't know if this is going to work here. Yeah, that's what I'm going to try. I'm going to go back. Yeah, I didn't think so. Work with me. So if we take HCl and add it to water, we get H plus and Cl minus. If we looked at this situation, do we look at an equilibrium? Son of a... Are you going to listen to me yet? That looks promising. Okay. HCl and we add it to water. Do we look at an equilibrium? No. It's a strong acid. It completely dissociates into the ions. So when we look at that, we're done. Completely H plus. Where you might be considering is if we went through and said, let's take ammonium chloride. Whoops. I don't want a plus there yet. It's an eraser. We take ammonium chloride, add it to water. What's the first thing that we do? Dissociate into the ions. What are our ions? NH4 plus, because we've got that complex ion situation. We've got to go into our ions first. Chloride. Now when we go through, we want to see how each of those ions reacts with water. If we take a look at NH4 plus, and we react it with water, what do we get? NH3 and H3O plus. So at this point, we've assumed a reaction occurs. So now what we go back and do is say, okay, was it fair to make that assumption? Is NH3 a strong acid or base? No. Which means we do have an equilibrium, which means we do have an effect on the pH. Now let's go through and take a look at the chloride ion. What happens when we add the chloride ion? That's a chloride. To water. Let's first assume the reaction occurs so that we can see the products. What happens? HCl plus OH minus. So we could now start to look at the effects on the pH, but before we do that, we want to make sure that this species is not a strong acid or base. Is it a strong acid or base? Yes. Which means, do we reach equilibrium? No. According to that being a strong acid, which way does the equilibrium lie? To the left. Back to our acid. Or sorry, back to our chloride ion. Okay. There it's to the left. Why is it to... Where'd it go? Is it under here? Why would we consider it going to the right here? What equation are we looking at? We're taking HCl plus water going to H3O plus Cl minus. Which way does our equilibrium lie in this reaction? To the right. Okay? So there's no left in this case because what we're looking at is the strong acid here. In this case up here, we were evaluating how the chloride ion affected the pH. It's an entirely different problem. The chloride ion has no effect on the pH because it generates a strong acid. Here we're starting with a strong acid. Go straight across. Does that make sense? So that at least fixes you. Does that fix your question about the left?
Yeah.
Kind of? Okay. That's what you're asking about? Okay. So yeah, it's looking at a different problem. It's the effect of each of those individual ions. When you see a strong acid, don't look at it necessarily as HCl, but really we should write this out as H+. So that when we go through and solve this, we have the strong acid left over. There's no need to go through and do any equilibrium stuff over there because I've got acid already. Nothing to worry about.
You only do the ice chart if there's not a strong acid.
Yes. Okay. Aren't buffers fun? Okay. In case you couldn't tell already, these are going to take lots of practice. Please take me back. To go through and do these perfectly when it comes to the exam. Writing it all out requires a lot of space and a lot of preparation to go through and do it. Okay? Please practice it so that when you get to the exam, you can write it out appropriately. Worst case, when you see the problem, scribble some information down. Force me to try and give you some extra credit. If you write nothing down, not extra credit, give you any credit. If you write nothing down, how much credit do you get? Absolutely nothing. I have no choice but to give you no points. If you give me something to look at, you increase the likelihood that I will potentially give you points. Yes?
So for strong bases, should we assume that they're OH?
Yep. For strong bases, you would immediately jump to OH minus. Okay. More questions on that? Yes.
In D, underneath the reaction, it's 0.2 minus 0.1. Why is it minus 0.1? Is that because it's reacting with the NEF?
When we do to the reaction section, it's always going to be a subtraction. What are we subtracting? The smallest number. Which one's smaller, 0.2 or 0.1? 0.1. That's the one we subtract. That's our limiting reagent. Other questions on this? Lots of fun. Okay. Those of you doing lab, this is the lab you're doing, technically. Okay. So, if we went through to try and come up with a curve for this, what did we say the pH was with just the sodium fluoride? What did you say it was? It said 8.08, right? Okay, if we add some acid, the pH drops substantially. Okay, when we did our first, so let's call this one C. Okay, what happened? The pH dropped a lot, went down to all the way down to what, 2.17? Did I do that right? It was 2 something, wasn't it? Okay, 1.9. Everybody's saying 2.1, so let's just say 2.1. That way I can be okay. We went through and did the C partial, and in that case, now I don't remember which one of these this was. Shoot, I can't directly tie these. These aren't going to work that way. So let's just go through with our own numbers. What happened? Where did we start with our pH? Before we added any acid? Pretty high. It was basic. So if we're going to try to draw a titration curve, we could start up pretty high. Okay, what happened as we added acid? It started to drop. Okay, how sharply did it drop? Okay, we have to be a little bit careful with that because we added quite a bit of acid to get that big drop to begin with. Okay, so what we got was a drop, kind of levels, and then it sharply dropped. At that sharp drop, what happened? The acid overcame the fluoride ion, which then means this leveled off again. Okay, because now we can't add any more acid to the solution. We keep adding acid to it, but eventually it levels out because the water can't physically hold any more acid. So we could go through and identify interesting pieces on this. Okay, what happened at that point? Jay, you said it earlier. What happened? The acid overcame our initial base. Okay? So at this point, the acid added is equal to the base that we started with. Because we call it equal, we've got an equivalence point. Okay, where those two things equaled each other. Kind of nice. One of the more interesting aspects of this curve, which is what we ended up solving for, not C, or C prime, if we will, with all the black stuff going through this. What happened at that point? Our pH became what? Based on our H plus concentration. Our H plus concentration was, what did this number, where did this number come from? The Ka. So interesting. Our pH equaled the pKa in that example. Didn't work in all examples, but in that particular example it did. So what we could do is go back through and try and determine when that occurred. Okay, at that point, we said what about the concentration of HF and the concentration of fluoride? What were those concentrations? They were equal to each other. When would they become equal to each other? At the equivalence point, we have no fluoride ion. We've converted it all over to HF, okay, which is why there's nothing to balance the acid added. What about at our very beginning point? What's at that very beginning point? What's the only thing I've got up here? I've got the fluoride ion. What happened at the equivalence point? There's now no more fluoride ion, so now it's only HF. I want the point where HF equals the concentration of the fluoride ion. Where is that?
Question.
Yep.
Wouldn't the equivalence point be right where it drops off? Because when you run out of the fluoride ion, then it's going to
That's
drastically change. So where
that's
does it
the
go?
middle of that point. So what we're looking at in that situation is the balance very quickly between them. So it's actually halfway in between. It is that equivalence point. Where does it exactly drop off? Here it's starting to drop, but it's dropping here too. Isn't it dropping here as well? Where does it completely drop off? Right in the middle. What happens after that point? It starts to level out again. So it's the inversion point of those two curves. This one is, what is that, aimed downwards? This one's aimed upwards, if you will. So that inversion point is where your equivalence point is, where it's completely transitioned across. So where do I get HF and F minus concentrations equaling each other? The equivalence, I only have HF, and at the beginning, I only have F. At the exact middle of that, which is known as the middle is a good way to think about it. We could call it the middle equivalence point. Someone decided to get a little bit fancier with it. It's halfway to the equivalence point, so it's the half equivalence point. What happens at that point? This pH equals the pKa, or the pKb in this case, because we're looking at the base. Okay, so this one gets a little bit trickier. Okay? So we can start to pull information off of a titration curve, which is what... Ooh, I didn't want to show all that. Let's back away from that. So in all of these buffer situations... Oh, man. No, don't do that. All of these buffer situations, we end up ultimately solving for the pH. Yes?
The equivalence point, what are we saying HF is equivalent to if you say there's only HF?
It's equal to the initial moles of fluoride that you started with, because it's all completely converted across. In all of these cases, we were relating the equilibrium constant to our equilibrium concentration. So we're looking at a Ka. which was H3O plus times the concentration of what? Careful. What reaction generates an acid dissociation constant? HA goes to H3O plus our conjugate base. Products over reactants. Okay. I want to solve for the pH. That's ultimately all of these goals. How do I solve for a pH? In general, negative log of the H plus. Okay. Do I have the concentration of H plus in this equation? Effectively, it's the H3O plus. So instead of going through and solving all of this ice chart stuff, which is what you should do, somebody really smart came along and said, you know what, I don't want to do all that. I'm going to try and solve from the pH immediately. To do that, we need to take the negative log of the H plus concentration. So how can I do that? I need to get the negative log incorporated into this equation. How do we incorporate something? Do it to both sides. Negative log of the Ka will equal the negative log of this huge beast of a thing, which I'm going to abbreviate as H plus now. What's the negative log of the Ka equal to? All right, now what we're going to do is pull some equalities out of our log expression. We can say that this is equal to the negative log of the concentration of H plus the negative log of A minus over HA. Why would I do that? We don't quite see a straight line necessarily on this. What's the negative log of H plus? Distribute that minus out. What happens at our half equivalence point? What did we say? Concentration of our conjugate base equaled the concentration of our acid. Right? Those concentrations are equal to each other. Let's say it's 2 and 2. What is that? 2 divided by 2 is? What is log of 1? 0. What is the pKa equal to in that case? The pH. This expression, or versions of it, are known as the Henderson-Hasselbalch equation. Why is that a really helpful expression? When we go back to this ice chart, we assume that X is really, really small. So what's the equilibrium concentration of fluoride? If X is really, really small? 0.045, which happens to also be the initial concentration. Do I need to solve the ice chart at all? No. pKa equals the pH minus the log of those concentrations. I can plug in those concentrations, my initial concentrations, into this expression. When I solve, what do I find? pH equals the pKa. I didn't have to do any of that ice chart tabulation because we went through and mathematically solved for what that expression comes out to. Okay? One of the reasons why I dislike this equation, if we change this to, say, the Kb, we'll end up with a very similar expression. What's the one difference? These two things will be on opposite sides of the equation, or opposite sides of the fraction. Okay? So it ends up looking very different, okay, even though it's mathematically equivalent. It is, I believe, on your cheat sheet, so if you want to use it, feel free to go ahead and use it. The other reason why it's difficult is, at least in the old textbook, it said A minus was base, and it called HA acid. Why is that problematic? In this equation, or this problem, how many acids are there? There's a strong acid and a weak acid. Which acid goes into the pKa, or our Henderson-Hasselbalch equation? The weak acid. Okay? So you have to be very careful with the terms that you end up using. It's very easy to substitute the wrong numbers in. The Henderson-Hasselbalch equation only refers to our initial concentrations of our weak acids and our weak bases. So be careful with those applications. Okay? It can help solve a lot of these buffer things. That expression, which we just solved for, you'll notice it's slightly rearranged. I shuffled it around to solve for the pH, because in most cases we want the pH. Okay? The observation that we pull from this we've already seen. If our concentration of our conjugate base and our acid are equal to each other, we find out that the pH is equal to the pKa. That is, by definition, our half equivalence point. Okay? Up to you on whether or not you want to use that expression. Again, remember, you must be very, very careful, with how you input it in there. You can already see I wasn't as careful. Okay? So, 2 options to go through and solve. All of them involve the barn chart. Every single one of your buffers. You must go through and determine your limiting reagents to figure out what your initial concentrations are. Once you know those initial concentrations, then you can go through and either use the Henderson-Hasselbalch expression or you can use an ice chart. Both of them will give you the exact same answer. Okay? So, you can expect one problem like that. You can expect to interpret a ice chart, or not an ice chart, a titration curve as well, okay, as far as your exam goes. So if we take a look at some titration curves, these are the easier ones to evaluate because we see these more typically. What did we start with? How do you know we started with a weak acid? pH is low. Okay, how else do you know? What do we add to it? A base. What do bases react with? Acid. Okay? So what information can we pull off of this? We've got our titration curves. Where's our equivalence point? Our equivalence point is right where everything goes sharply upwards. So it's along this line. Oh, that didn't fit in there. Where's our half equivalence point? Half of the base that we've added. How much base did we add at this point? 50. So our half equivalence point is 25. What's the pKa of the yellow line? We go to our half equivalence point. The pKa of our yellow line is 4. We now have information about that acid without having to do any calculations. Okay? So that interpretation becomes really, really helpful as far as being able to analyze these. You end up doing that in lab, is determining that half equivalence point. Yes?
Why do we consider, say, line 50 the equivalence point? Does the equivalence mean that they're both like equal to each other?
When the amount of base added equals the amount of acid that you started with. So in this case, they had equal concentrations of everything, and so they all came out at the same value. So if I start with a 1 molar solution of the acid, whether it's weak or strong, the equivalence point is going to be when I get rid of all of the acid, which will be the exact same amount of base for every single acid I use. So all they're trying to do is make it easier to see. Your equivalence point for all of these, because all of these started with the exact same molarity, which means they're going to require the exact same amount of base to get to the equivalence point once we've reacted all of the acid. Okay? So we got our Ka points on there. I do want to address a little bit in solubility here, just to get an idea of what's happening. I have a feeling we're going to cut some stuff out of the exam because we're not going to get through the next 14 slides probably tomorrow, because I'm going to guess you guys have some questions about solving some stuff. So we can go through and work some problems tomorrow. I'll push through probably another 7 to 10 slides tomorrow. So wherever we end with our discussion on solubility, that's where you'll be responsible for. I'll try and tie it to the textbook so I can tell you where our cutoff is. Okay? The homework is still going to cover the whole textbook. I'm not about to double back through the homework and start pulling questions from it. Okay? So, solubility. What ends up happening with this? According to 151, we had all of these rules. And when we look at these rules, we said some compounds were soluble or insoluble. We saw it as black and white. It's either dissolves entirely or it doesn't dissolve. Okay? Which is nice. That made 151 easier. We either had it's this unit or this unit. There's no gray area in between. When we move into 152, it's a little bit different. Okay? So if we looked at an example for 151, we said we take those ions, okay, we look at our solubility rules, and our solubility rules say that that should make a solid. So we draw a reaction arrow, boom, solid, done. Okay, what happens when we move into 152? We actually go through and say, it's not really the case. Everything has some solubility. Okay? So what we do instead is take a look at that solid. Once we've got it in solution, it can now ionize into the individual species. Okay? So we look at the equilibrium of that solid compound dissolving. So what would an equilibrium expression be for that? Okay, good place to start. Equals concentration of our products over the reactants. Should I draw the reactants? No, why not? It's a solid. Okay? So our equilibrium expression is only dependent on the ions generated. One of the things that makes this chapter tricky is that these coefficients don't necessarily have to be 1. Which means when you go through and look at your equilibrium expression, you have to translate those coefficients to your superscripts, okay, your exponential values. Okay? Oh, I actually drew it there, and we could cross out our silver chloride solid. Okay? So just we'll come back to solubility. We'll start with that tomorrow. I did want to cover this. Okay? When it gets into units so that you can actually work some problems with this, solubility gets trickier because of the units that we end up using. Solubility is something that's very, very ancient and not very technologically savvy, I would guess, or one way to phrase it, which means we didn't have a real concept of moles or atoms in that case. We only had what we could weigh out and how much we could dissolve it in. So typically, when you look at the units for solubility, they almost always give it to you in grams of whatever you're trying to dissolve, or your solute divided by the milliliters of your solvent. Okay? So be aware that when you try and solve problems, you may see these odd units. What's the problem with those units? This is an equilibrium solve. What units do we use when we deal with equilibrium? Concentration in molarity, which means to use an ice chart, you must convert those grams per milliliter into moles per liter. Okay? Be aware of that conversion. It's ultimately the same idea as we've been going through before. It's just another application of it. Most of it is just kind of an English spin on it. How do you end up changing what we're referring to? We will go through and solve some of those, and we'll talk about some more of the intricacies with each of those tomorrow.